see what we got going here. So our pictures are such that you have picture here, got this area, it's coming around, so we get this shape, and then when we cut perpendicular to our axis of rotation, means we're taking and cutting perpendicular to our axis of rotation. And so you guys are getting your radius. Oh, it's not bad, huh? That first one, what did you get for that integral? Ella, what did you get? Volume is?
I had like what? Sorry, I had from
1 to 2, because you're cutting perpendicular to the x-axis, so you're integrating with respect to x, and then pi e to the x squared. Perfect. And so then you go to integrate it, which is going to be e to the 2x. Is that what you did? And then you did the antiderivative. And so everybody's getting pi over 2 times e to the 2x from 1 to 2. And so your final answer is going to have e's in it. I think it's e to the 4th minus e squared. Is that what you guys are getting? Times pi over 2 cubic units. But what's important is the setup. How are you guys with this problem with the setup? Is that okay? Everything okay with that? And then the second problem, on the second problem, you had a similar shape, but this time we were going about the y-axis. And so this time when you set your circles, they're sideways circles. And so the radius of every sideways circle sits sideways this time. And so we integrate on the y-axis. Alex, did you get an integral for this guy?
Yeah.
Can you give it to me? What'd you get? Integral from?
0 to square root 2.
I love it. I love it. And we're going to integrate with respect to y. And then what'd you have as your radius?
Y squared plus 1.
Ah, absolutely. Because we're in, and then you squared that sucker, right? And how did you do that? Because you noticed you're integrating with respect to y, so you need to convert him. So you made y squared equals x minus 1, and that became y squared plus 1 is x, and that's where we got our inner radius that time. Beautiful. And then you multiplied this out, and ew, it's a messy number. I know it's a messy number. So I get y to the 4th plus 2y squared plus 1, undo Tina, 1, and then you integrate it. And everybody's getting, let's see, pi times. You get 1/5 y to the 5th plus 2/3 y cubed plus y. And we're integrating from 0 to square root of 2. And so you guys have, 4 square root 2 over 5 plus 4 square root 2 over 3 plus square root of 2 cubic units. And then if we want, we can get a common denominator and put it together if you want to. I think that'll be 15. And so then that will be 15 plus 20 is 35 plus 12. 47? No, I did that wrong. Did anybody get a common denominator? Did I mess up? I might have messed up. Hang on. Did I mess up? I think I'm okay. 32 plus 50. I get 47. I'm getting 47 over 15 times the square root of 2. Oh. But I'm okay with the one above it. I'm okay with the one above. Did I do that right? Is that good? Questions on the warm-ups. Let's find the volume of the solid obtained by rotating the region bounded by the curves y equal e to the x, x equals 2, x equals 1, and y equals 0 about the y-axis. So let's see. And the problem is, if we start using washers, it's okay, we can use washers, but we got a couple problems. First problem is this. When I'm cutting my washers up to here, I would have an outer radius and an inner radius. But then when I get to here, at E, now it switches. So I have an outer radius and a different inner radius. So I would have to integrate with respect to 0 to E and do outer minus inner, which is okay. And then I'd have to go E to, what would we have to go up here to? E squared. Okay, and that's okay. And then I have outer radius squared minus inner radius squared. But then what do I have to do? I have to solve for x and write it as x equals the natural log of y. Are y'all with me? And so then we'd be integrating natural log of y squared. We do not have the ability in Calculus 2 to integrate the natural log of y squared unless we plug it into a computer. Okay? We don't have a technique to help us out. So we're stuck. We can't really use this method if we're going to use washer method with the techniques we have in Calc 2, which means we need another method to integrate this other than cutting and chopping it up into washers. So what we're going to talk about is a method where instead of cutting perpendicular to our axis of rotation, which would give us washers, we're going to cut parallel to our axis of rotation. So instead of cutting perpendicular to our axis of rotation, we're going to cut parallel, and I'm going to write this down, we're going to cut parallel to our axis of rotation. And when you do that, what happens? When I make a cut parallel, what I actually mean is I'm going to completely cut all the way around parallel to my axis of rotation. So I have a little manipulative. It's not perfect because my son it got stuck, and I made him make me new ones. But so we have an axis of rotation, and we're going around this axis of rotation. And the idea is instead of cutting perpendicular, we're going to cut parallel. And when you cut parallel, you're actually going to cut all the way around. So you're going to take this cut, and you're going to go all the way around. And so what you're going to do is make these little slices. So I'm going to take and I'm going to cut all the way around, but I'm going to get these little slices. Do you see how you're going to get little slices in here? But these little slices are actually miniature cylinders. Let's see if you guys can see that. And I have, if you get on Canvas, is anybody on Canvas right now? If you get on Canvas, I was going to pull it up and show you. But on Canvas, I have a Desmos and a GeoGebra link, and I can actually, it kind of shows you how these cylinders will sit. And so what happens is, if you cut parallel to your axis of rotation, what you get is a cylinder, and if you can picture it, you can start stacking these cylinders and just making them bigger and bigger and bigger, right? Filling these cylinders in, and it can fill in the entire volume. They'll just get a little taller as they go outwards. So what's happening is you're taking cylinders and you're stacking them, and they're going to have different heights, okay? They're going to have different heights. These cylinders are going to have different heights, but when you put them all together, it's going to create a volume for this shape, okay? So that's the idea of what's happening with cylindrical shells. And like I said, in Canvas, I do have notes. Let me pull this up here quick. Let me see if I can get it really fast. Martin Christina at etown.edu. Superstar for math 3D68. But when we look at these cylinders, oh, he's taking too long for me. Well, all right, I'm just going to let it be. I'll show you a picture then. But trust me, when you stack vertical and you take your cut and draw, you should get a cylinder. And so what we're going to do is we're now going to integrate, and not discs or washers, but we are going to integrate cylinders. And that's called the method of cylindrical shell. Now, all right, so now let's talk a little bit. Okay, first of all, what is the advantage of cutting parallel to an axis of rotation versus perpendicular? Well, for a problem like this, when I cut parallel to my axis of rotation, notice, where am I cutting? What am I cutting along? And I'm stacking these cylinders along. What axis am I stacking all these cylinders along, right? Let me get another one. Let me get a red one. So I'm going to put another cylinder in here. And then I'm going to get another cylinder. So let's get orange. And he comes in here. And that's another cylinder. And then I'm going to stack on top of that another cylinder. We'll make him green. And so he's another cylinder. And so the idea is we're stacking all of these cylinders, these shells, and we're putting them all together, right? But when I'm cutting, what am I cutting along? I'm cutting along, I'm stacking them along, not stacking them sideways along the y-axis, I'm stacking them along the x-axis. Do you see that? Which allows us, instead of having to go and integrate with respect to y and change everything over into the natural log, I am instead going to integrate with respect to x. And so what cylindrical shells allow us to do is keep x as our variable of integration for this problem, which makes it really nice because then my limits are really clear. They're going to be what to what? My limits are just going to be 1 to 2. But more important than that, I can just use this function e to the x and not have to take natural log of y squared. So it allows me to stay with an integral of x as my integral of variable of integration. So we've done a lot of integration. We started out with semicircles, and we figured out what that was. And then we did equilateral triangles. Remember this. And then we also stacked squares in here. And then we did discs. And we also did washers. But now what I'm saying is we're going to integrate shells. And when I say shells, I mean the surface area, not the volume of the shell. So what I want is the surface area. I want the surface area, because I'm doing an area, right? I want the surface area for this cylinder. And so what is the surface area of a cylinder? What is the surface area of a cylinder? Let's make a cylinder. Cylinder, right? Very close. Yes, yes it is, yes it is, yes it is. So for a cylinder, if I want the surface area, that means I just want the area around the outside. But every cylinder can be made by taking a rectangle or cutting, opening it up. Every cylinder is in fact a rectangle, right? So if I'm looking for the area of a cylinder, I'm just looking for the area of the rectangle. And the area of the rectangle on a cylinder is going to be its height times its length. And what is the length? The length is just the circumference. Do you guys see that the length of that cylinder is just the, are you with me on that, circumference? And what is the circumference, Noah, of a circle? It's 2 pi r. So to get the area for a cylinder, the surface area for a cylinder, we are simply taking, beautiful, 2 pi r times h, because every cylinder can be opened up into a rectangle. If I was to cut right along the edge and open it up, I get this rectangle. And this rectangle, this cylinder has a height defined by h, and then it has this length, and that's defined by the distance around the circle, which is 2 pi r. Hence, the surface area of every cylinder is 2 pi r h. And so this creates our new formula now for volumes with cylindrical shells. 2 pi r h dx, where h is the height of the cylinder, and r is my radius. Now it's pretty clear what my height is for this particular cylinder. The height is this distance here in my picture, which is defined by this distance right here. So what do you think the height is for this particular cylinder?
Y equals e to the x.
I think so too. I think my height for my cylinder here is e to the x. Now the radius sometimes gets people a little messed up, a little confused, but I think of it this way. In my picture, I just picked a random cylinder. Do you see I picked a random cylinder? Could you approximate what the radius is for that cylinder? What is that radius? Could you approximate how long that is for this particular cylinder that I drew? It's about 1.5. Now, where did you look to get that? On the x-axis, didn't you? And if I move my cylinder over a little more, I would still look along the x-axis to determine what the radius is. And in fact, when you use this cylindrical shell method, your radius will match your variable of integration. It's just x in this case. The only time it will change, because you're just cutting it along the x-axis. So you are just getting this distance, which is a movement along the x-axis. The only time it's going to change and not the x is if, for instance, instead of rotating around the y-axis, I was going like around the line x equals -10. Now all of a sudden I've got a big different radius going on. You know what I mean? Like if I move my axis of rotation, then that's going to change. But otherwise, you will find with cylindrical shells, your radius will always be your variable of integration. It's going to match your variable of integration. So this integral right here solves and gets me the volume for this shape. Beautiful. You guys want to try and evaluate that out for me? So let's see. So we're actually going to using cylindrical shells, we're going to go from 1 to 2. Those are my limits of integration along the x-axis, and we're simply going to take 2 pi times my radius, which we just said is just a measurement of x, times e to the x. Oh yeah. How do I integrate this sucker? You got it? Can I use U-sub?
Integration by parts.
You got it, I know you got it.
Is integration.
Integration by parts? Integration by parts? Absolutely, thank you. Very nice. Integration by parts, I like it. UV minus the integral of V du? I have some Excedrin, Aiden. Do you want some Excedrin? Are you sure? They help with the fever and they help with the head and the headaches.
So if you were going around like a different like x, what would that look like if you went around like
So-
x equals -2?
Okay, so let's say we go around x equals -2. Now my cylinder gets a little bigger. So it still is a measurement along the x-axis, but now I'm going to have to add to it
Okay.
2 more units.
X minus.
So it's x minus -2, right? Because it's the one side minus the other side.
Okay, got it.
Does that make sense?
Yeah. So then you would just like.
Yeah, and so if I did the same thing, what if I took that shape? You've got it, Ella. What if I took that shape and let's say it went around x equals 5?
X minus.
So now my radius this time goes this way. Now, normally we go this way as x.
Yeah.
And so if I'm going this way, it's going to be 5 minus x. You see how 5 take away those x's gives me the leftover piece. Yep, but always x is the radius too. Yeah, good questions, good questions. Awesome. You guys are using integration by parts? And you're going to let u equal x and dv be e to the x dx. And so I think, and then it's uv minus the integral of v du. And so what we're getting is we are getting 2 pi times the integral of uv minus the integral of v du. And we're going to go from 1 to 2. And then we integrate that out. So we've got x e to the x minus e to the x from 1 to 2. we're getting 2 pi times, let's see, that's 2e squared minus e squared minus 1e to the 1 plus e to the 1. Those cancel. So that's going to give me 2 pi times 2e squared minus 1e squared is 1e squared, which gives me 2 pi e squared. And that's the volume for that shape. Who's got a question? I do have a page that shows you all these cylinders sitting. And so if you follow along in your notes, it kind of breaks it down and shows you where the cylinder's coming from. And online in Canvas, if you look, there is a Desmos and a GeoGebra example where you can go in and play with it, and you can actually play with making different cylinders. So if that's something you like to do, it's on Canvas. But I think we're going to practice a couple problems. You want to practice a couple problems? We'll practice a couple and get my front up down a little bit so you can see this. So what I want to do this time is use the method of cylindrical shells to find the volume of the napkin ring obtained by rotating the shaded part of the circle where x ranges from 6 to 10. So that means that it's going from 6 to 10 along the x-axis is what it's saying. And what they want us to do is rotate this green shaded part about the y-axis. And can you see that when you take that green shaded part about the y-axis, you get like almost like a bangle bracelet. Like, I wish I had one of those. Some people I've seen wear those like bracelets that are kind of like bangles. They also call it a napkin ring. So this is like one of your homework problems. It looks like a napkin ring. But if I take that shape and rotate it about the, if I take that shape and now rotate that sucker about the y-axis, I get this shape that comes around. So it's like this bracelet. It's like a bracelet kind of idea where you get this thing going around. And instead of cutting perpendicular to our axis of rotation, they're telling us to use cylindrical shells and cut parallel to our axis of rotation. And so when we go to cut, you want to cut parallel to your axis of rotation and come around. So your cylinder is sitting like this around here on the side. So you have all these cylinders that come around. But notice, again, you're cutting along the x-axis. So that means we get to integrate along the x-axis. So we get to integrate. I'm going to wander and see how you guys are. So we've got the top function, and then we've got the bottom function, which is a different curve. And so we got our top function, we got our bottom function. So to get the height, we have to go between those two. And they're both going to come from x squared plus y squared is 100. So we got x squared plus y squared is 100. And so if I want to solve for y, I get 100 minus x squared. So I'm getting y is plus or minus the square root of 100 minus x squared. So positive on top and negative on the bottom. And so the height is the distance between the two, which is going to be the top function minus the bottom function, which I think is actually going to give me 2 of these square roots. Is that what you're getting? 2 of those square roots. So when I go to set up my integral, what did you guys put for your limits of integration? 6 to 10. Beautiful, because those are the ones on the x-axis that are bounding my region. 6 to 10. 2 pi. Radius is just x because that's my variable of integration, and it's also the distance from the y-axis. And then the height is 2 times the square root of 100 minus x squared dx. So your integral that you're actually calculating the volume with is 4 pi x times the square root of 100 minus x squared. What method? What did you use there, Noah? You used what on that? U sub. I would use U sub as well. I would let U equal 100 minus x squared. That's exactly what I would do. And I also like to change my limits. Not everybody does. So it's up to you if you change your limits. So U is 100 minus x squared. So that would be 100 minus 10 squared would give me a 0. And my bottom limit is 100 minus 6 squared, which is 100 minus 36, which is 64. So if you so choose to change your limits, you would get 64 to 0, negative 1/2, square root of u du. And, oops, make sure I'm going to get rid of this negative 1/2 and switch my integral limits. So that's going to be 4 pi, 0 to 64, u to the 1/2 with a 2. I'm getting 64 to the 3/2 times 4 pi over 3. And 64 to the 3/2 is the same thing as the square root of 64 cubed, which is 8 cubed, which is 64 times 8, which is 512. 4 pi over 3 times 512. 6 plus 3 does not go into 512. So if I wanted to work it through, I think I get 2048 pi over 3. I guess what I get. See if you guys are all good. I was going to wonder, who's got questions? Who's got questions? Good, pardon? Yeah, so do I have one of those? Let me see if I have one of those. There we go. Yep, there it is. Y equals square root of x minus 1, y equal 2, x equals 0, and y equals 0, but I want us to send this about the x-axis. So I want that region about the x-axis. Five minus 1 is 4, and 4 square root of 4 is 2. This is 1, this is this. It goes like this. So 3 actually gives me square root of 2. I want to go about the x-axis. And like I said, we could use washers on this one. We really could, but I want to purposefully use cylindrical shells on this one. so this time you can kind of see, right, with shells we always cut parallel to our axis of rotation. And so you'll see your cylinders are sitting sideways now. And so now your height moves this way, and now your radius is the one that moves up and down. Basically, your radius will always be perpendicular to your axis of rotation. No matter what method, your radius is always perpendicular to your axis of rotation because you're going around that thing. But in this case, a radius is defining this, and the height is this. And so can you guys see kind of what's going on here? Set that up and see if you get an answer. I'm going to wander around. Make sure you guys got at least a setup, okay? So the height is going to depend on where you're at, because these cylinders are going to get bigger, right? So your height is defined by this distance, this horizontal distance here, which actually is your function on the right side. Do you see that, Arden? So that's y equals square root x minus 1. That's going to define my height. But first of all, because I'm going this way and cutting, I am cutting along the y-axis. So very first, everybody should be putting 0 to square root of 2 dy as my variables of integration. And then my height is defined by that side equation, which is y equals square root, but we have to turn it in terms of, so we got y squared plus 1. That's going to be my equation here, minus 0. So that's going to be my height. My height is just y squared plus 1. And then the radius will always match your variable of integration unless you're going around a different line. So my radius will always match my variable of integration because it's a measurement along the y-axis. And so that means I have 2 pi y times y squared plus 1. And so then I would just integrate this sucker, and I would get 2 pi times y cubed plus y. And we're going to keep going. And I think your final answer should be 4 pi if you've done this correctly. 1/4 y to the 4th plus 1/2 y squared from 0 to square root of 2. So I'm getting, square root of 2 to the 4th is 4 over 4. 1 plus, and then square root of 2 squared is 2 over 2, 1. So 1 plus 1 is 2. 2 times 2 pi is 4 pi. I'm getting 4 pi cubic units.